In this lesson, we will look at the construction and operation of electric motors using AC as their power supply. The great advantage that an AC motor has over its DC counterpart is that it doesn't require the use of a commutator, so the problems of arcing at the brushes is greatly reduced or even eliminated. Whether the AC motor is single or multi-phase, the principle of operation is the same. The motor is made up of a stationary part known as the stator and a rotating assembly known as the rotor. The stator is most commonly fed from a three-phase AC supply. The stator windings are set 120 degrees apart, with the pair of poles for each winding being supplied from one of the three phases. This arrangement produces a rotating magnetic field around the stator. To see how the rotating magnetic field is produced, we will look at one half cycle of the AC supply. When the current flow in their phases is positive, the poles marked A, B and C are magnetic north poles, and those marked A1, B1 and C1 are south poles. When a phase's current flow is negative, its magnetic poles are reversed, with A1, B1 and C1 becoming magnetic north poles and A, B and C becoming souths. If we start at point 1 on the graph, you can see that phase A is at its positive peak. So, pole A has a strong north magnetic pole, and A1 a strong south pole. Phases B and C are both negative, so poles B1 and C1 have weaker north poles. The magnetic fields will look like this. If we move the sequence on to part 2, we can see that the C phase current is now at its negative peak, so the C1 to C magnetic field is at its strongest. A phase has moved away from its peak, so the strength of the A and A1 magnetic poles is reducing, and B phase has moved from negative to positive. So now pole B is now a north, and pole B1 a south. Moving on to position 3, B phase is now at its positive peak, so there is a strong magnetic field from pole B to B1. Both A and C phases are negative, so poles A1 and C1 are weak norths. At position 4, A phase is now at its negative peak, so there is a strong magnetic field from pole A1 to A. B and C phases are both positive, so poles B and C are weak norths. This process continues as each phase moves through its cycle, causing the total magnetic field to rotate at a speed equal to the frequency of the supply. If two phases of the supply to a three-phase rotating field are reversed, the direction of rotation of the field, and thus that of the rotor being driven by it, will be reversed. There are two types of rotating field AC motors in common use in aircraft installations. They are known as synchronous motors and induction motors. We will look at them both, beginning with induction motors. The induction motor gets its name from the fact that an alternating current is induced in the rotor by the rotating magnetic field in the stator. It is the most commonly used AC motor because of its simplicity, its robustness, and because it is relatively cheap to produce. The rotor usually consists of a cylindrical laminated iron core which has a number of longitudinal bars of copper evenly spaced around the circumference. These bars are joined at either end by rings of the same material to form a composite structure called, because of its shape, a squirrel cage. The rotor bars are made of very low resistance material so that a large current can flow through them. The rotating magnetic field produced in the stator cuts through the bars of the rotor, which along with the end rings form a closed circuit of low resistance. The resultant induced voltage creates a relatively large current flow in the squirrel cage assembly, as shown in this simplified diagram. This current flow sets up its own magnetic field, which interacts with the rotating field of the stator to produce a torque, causing the rotor to turn in the same direction as the rotating field of the stator. The speed of an induction motor is determined by the frequency of the supply and the load on the motor. The rotor never quite reaches the speed of the rotating field. The reason for this is because if it did, then the squirrel cage bars would not be cut by any lines of flux from the rotating field, and no voltage would be induced in them. The difference between the speed of the rotating field, or the synchronous speed, as it is known, and rotor speed is called the slip speed, or rotor slip. Because of the difference in speed between the stator field and rotor, the induction motor is sometimes referred to as being asynchronous. If the load on the motor is increased, the rotor will tend to slow down. This will increase the amount of cutting of lines of flux and increase the current flowing in the squirrel cage, which in turn increases the strength of the induced magnetic field, which increases the motor torque to compensate for the increased load, maintaining the motor speed virtually constant. Most induction motors fitted on aircraft are of the three-phase type. However, single-phase induction motors can also be used. Single-phase induction motors are not self-starting. That is to say, when power is applied, they will not rotate. The most common method of starting a single-phase induction motor is by use of a split-phase winding at 90 degrees to the main winding. The current in the split-phase winding is made to lead or lag the current in the main winding by 90 degrees in order to change the pulsating field into a rotating one. This can be done by the use of capacitors, inductors, or resistors. Occasionally, the failure of one phase of the supply to a three-phase induction motor does happen. If the motor is lightly loaded, then it will probably continue to run at about half its normal speed. The fault usually becomes apparent the next time an attempt is made to run the motor, when it will not start to rotate. If a bar magnet is suspended in a rotating magnetic field, it will lock into the field with its south pole staying with the rotating north pole and its north pole staying with the rotating south. The magnet will therefore rotate synchronously with the field, at the same speed as it. This is the principle of operation of the synchronous motor. A practical synchronous motor, rather than using a bar magnet, has a rotating coil on a soft iron core, energized with DC through slip rings, causing it to act as an electromagnet. In the same way as the bar magnet did, it lines up with the field created by the stator, and if the field turns, the rotor turns with it. The speed of rotation of a synchronous motor depends upon the frequency of the supply and the number of poles. Since in most cases the supply frequency is constant, then so is the motor speed. We can transpose the formula we use to calculate a generator's frequency to work out the speed of the motor in revolutions per minute, or RPM. If a synchronous motor with 4 poles is supplied with a constant frequency 400 Hz supply, it will rotate at a constant 12,000 RPM. One disadvantage of the synchronous motor is that it is not self-starting. To obtain the initial rotation, some induction windings have to be added to the rotor to assist in bringing it up to synchronous speed. This is often achieved by fitting a squirrel cage type assembly to the rotor. Synchronous motors are often used on aircraft to indicate engine RPM. A small 3-phase AC generator, known as a tacho generator, is driven by the engine, so that the frequency of its output will be directly proportional to engine speed. The electrical output is used to drive a synchronous motor in the RPM indicator. The operation of this instrument is fully explained in the instrument's lessons. That is the end of the lesson. Here is a summary of the main points. An AC motor is made up of 2 parts, a stationary stator and a rotating rotor. AC motors use a rotating magnetic field in the stator to drive the rotor. If 2 phases of the supply to a 3-phase rotating field are reversed, the direction of rotation of the field, and thus that of the rotor being driven by it, will be reversed. An alternating current is induced in the rotor of an induction motor by the rotating magnetic field in the stator. The difference between the speed of the rotating field of an induction motor and the speed of the rotor is known as the slip speed, or rotor slip. In a synchronous motor, the rotor rotates at the same speed as the rotating field. Here is the formula for calculating the speed of rotation of a synchronous motor.